Hello and welcome back. In this concept 16, we discuss about internal forces such as shear force and bending moment in structures. So the idea of shear force and bending moment will be explained using a problem. We have a beam AD resting on a roller at A and which is hinged at point D. And this beam is in static equilibrium under force, an external force of 6 kilonewton and a force couple of 9 kilonewton meter at location D. So we have to find the shear force and bending moment and normal force acting at a given cross section B, which is to the left of the external force 6 kilonewton. In order to solve this problem, the first step is to find the support reaction RA. To find RA, we have to uh, identify the free body diagram first, where in which we can show all the forces acting on the beam. Here, a normal reaction is acting at A because it is on a roller, and external force 6 kilonewton is acting at a point between B and C, which is 3 meters from A, and a force couple 9 kilonewton meter is acting at D, and the normal reaction RD, which is an inclined force whose magnitude and direction is unknown, is also shown in this free body diagram. So from the free body diagram, the unknowns are the normal reaction RA, and we don't know the magnitude of RA, but we know the direction of RA because which is in the J direction, and the reaction at D, we don't know the magnitude and direction. So in order to find one of the unknowns, we use the condition for static equilibrium, which is moment of all the forces about any arbitrary point. So we choose the point here as D because if you do that, we don't need to worry about the unknown RD in the equation because it is passing through that. So if you use this sigma of the sum of all the moments of forces about D equal to 0, which will result in an equation as indicated, where you can see that the first is a cross product of RA in the J direction, which is at an angle, which at a distance of 9 meters in the minus I direction. So it's R cross F. And the second one is 6 kilonewton. The R is minus 6I because it is minus 6 units in the minus I directions. Cross 6 kilonewton is acting in the minus J direction. Plus, this is an anti-clockwise moment force couple at D, so which is the K direction. So we add all of them together to 0. So this will expansion of this cross product will give you minus 9 RAK because we know that I cross J is K and this minus sign here, so it's 9 times RA. Similarly, this is 36K and this is 9K, from which we can solve RA as 5 kilonewton, which is the normal reaction at A. So now we need to find out the shear force and bending moment acting at a given cross section at B. So in order to do that, we imagine that we're cutting the beam into two pieces through the cross section through a plane that is passing through the point between B and C. So and then we have two pieces. The beam AD is now cut into two, AB and BD, but we are considering only the left half of the beam, which is AB. Now we have external force, which is a reaction at A is acting on that beam. And since we are cutting the beam to the left of 6 kilonewton, that we don't worry about the 6 kilonewton in the left part of the beam. But we are assuming that the beam is under static equilibrium by a force FB acting at the cross section and right to the B where we cut the beam. And also MB is the moment uh, acting, we assume a moment MB is acting at that cross section, so that the left cut section of the beam AB will be in static equilibrium. Now, we're assuming that this section AB is in static equilibrium by internal force FB and the moment MB. Now we use the condition for static equilibrium to find these unknowns. The first condition is sum of the forces on this left cut section is 0. So we have RA is acting and FB is acting. The sum of these two will be 0. And since we know RA, FB will be uh, minus RA, which is minus 5J kilonewton. And to find out the MB, we use the sigma M equal to 0. The sum of moments of all the forces 0. So we take moment about point B. So taking moment about point B means you're taking the cross product of the RA, R cross RA. And here the position of A from B is minus 3I to the left. So 5J is acting there, which is the RA. Plus MB. MB is the unknown moment acting, force couple acting at B. So from this we can solve for MB as 15 kilonewton meter in the K direction. Now the force we solved, the internal force we solved, FB, has two components, I and J. The vertical component, which is the J component of FB, is called shear force, and the horizontal component is called the normal force. The free couple moment MB at a given cross section B at B is called the bending moment at that cross section. Now, in this case, we have FB is minus 5J kilonewton. So we don't have a I component. So FB equals 5 minus 5J kilonewton is the shear force. So the normal force acting at section B is 0 because we don't have any I component. And the bending moment is 15K we from our previous solution. So this is the bending moment at section B. Now, what will happen if we cut the beam at C? So we are going to find out the bending moment, shear force, and normal force at a different section to the right of the external force 6 kilonewton, which is at C. So we're going to do the same procedure. We cut the beam at C. So the only difference here is when we do the free body diagram, we have an external force of 6 kilonewton acting on the cut section of beam AC. And we also have the reaction A, which is the same as the previous case. And in this case, we're assuming that the force, which is the internal force FC and the moment MC is acting at C so that the section AC, the beam section AC will be in static equilibrium. So to find the unknowns, we use the condition for static equilibrium as we discussed previously. So in this case, RA is acting and FC is acting and the external force 6 kilonewton is acting in the minus J direction, from which we can solve FC as 1 kilonewton in the J direction. So remember that when you move from point B to C, the shear force has changed. Shear force has changed because the value has changed from 5 Newton to kilonewton to 1 kilonewton from B to C. So we can also use the condition for static equilibrium for the moments. Some of the moments of forces equal to 0. Here, 5, which is the R cross F is minus 3I cross 5J about C plus the the couple moment MC equal to 0, from which we can solve the bending moment at C as 15K. Now here also the vertical component of FC is called the shear force and the normal component The horizontal component is called the normal force acting at C. So since FC has no I component, uh, this force is a shear force, and there is no normal component at C. The bending moment is 15 kilonewton. So the final answer is at a given cross section B, the shear force is minus 5J and the normal force is 0 and the bending moment is 15K. And at a different location C, the shear force is 1J kilonewton and shear force is which is 1J, shear force is 1J. Normal force is 0 because it has 0 I component and the bending moment is 15K. So we have a problem, another problem. So it is just repetition of the same problem. All you have to do is repeat the exercise with a slight change in the numbers. We have the external force 3 kilonewton in this case. And also the distance of the point of application of force has changed to 2 meters. So do this same procedure so you get final answers, and we'll check this answer in class. Finally, the third problem, we have the external force acting at an angle of 60 degree between a location of B and C. Find the normal force, shear force, and the bending moment acting at B and C separately. Follow the same procedure. Only difference here is since the external force inclined, you may find a normal force component and shear force component at B and C. We will solve this problem in class. Uh, Thank you.